Somewhere near you right now, there is a railway line, and running along it are two ribbons of steel that you have seen 1,000 times and never once truly examined. Do it mentally with me now. Slice a rail in half and look at the cut end. What you find there is genuinely strange. Not a solid bar, not a square, not a rectangle, not a cylinder. Instead, a peculiar silhouette, a fat, rounded crown at the top, a thin, pinched waist in the middle, and a wide, flat foot at the bottom, something like a capital letter I that spent too long at the gym. And here is what should stop you cold. That exact silhouette is universal. It carries bullet trains in Japan, coal trains in Australia, metros under Paris, and 3-kilometer freight monsters across the American plains. And it has stayed essentially frozen for close to 2 centuries, while everything around it, the locomotives, the signals, the speeds, transformed beyond recognition. Why that shape? Why the waist? Why the crown? Why the foot? The complete answer is one of the most elegant pieces of engineering hiding anywhere in your daily life. And I'm deliberately saving it for the end, because to appreciate it, you need to see everything that failed first. You'll also meet the man who carved this world-conquering design out of a piece of scrap wood with a knife in the middle of the ocean. And along the way, you'll learn 2 secrets almost nobody knows: that the top of a rail is not actually flat, and that the rails on a real track are not even standing up straight, both entirely on purpose. Hold those questions. We start in an era when railways were made of trees. Long before steam, in the 1700s, mines and quarries across Europe ran primitive wagonways, carts hauled by horses along parallel rails cut from timber. Wood was cheap and easy to shape, and it worked, briefly, because wood wears fast under loaded wheels. So operators nailed thin straps of iron along the top of the wooden rails as a protective skin, creating what history calls strap rail. And this cheap hybrid spread widely, especially across early America, where iron was scarce and forests were endless. It also created one of the most horrifying failure modes in transport history. Under repeated wheel pressure, the iron straps worked loose at one end, and the passing wheels would then curl them upward into hardened metal ribbons. Railroaders gave these a name that tells you everything: snakeheads. A snakehead could whip up through the wooden floor of a moving carriage like a spear, and in the 1830s and the 1840s, American newspapers carried accounts of passengers injured and killed exactly this way, impaled by their own track. Some lines took to inspecting constantly for loose straps, and passengers learned to eye the floorboards with genuine suspicion. Riding early rail was not just uncomfortable. The railway itself could attack you. And yet strap rail lingered for years in iron-starved regions, because a thin ribbon of metal, sometimes barely thicker than a finger, was all many operators could afford. Clearly, wood with an iron skin was a dead end. The next answer was solid cast iron, and it arrived with its own bad ideas. One school of thought said the track should do the steering. Engineers like Benjamin Outram laid what were called plateways, rails shaped like a capital L, with a vertical lip standing up along the inside edge so that plain, flat wheels, ordinary cartwheels, couldn't slide off. It sounded sensible, and it behaved terribly. That L-shaped groove was a perfect gutter for gravel, mud, ice, and coal spills, and every bit of debris packed against the lip became a little derailment machine. Meanwhile, cast iron itself was betraying everyone. It's a brittle material, strong when squeezed but treacherous when bent, and under the hammering of ever heavier loads, cast rails cracked and snapped without warning. Engineers fought back with geometry. In 1789, William Jessup introduced rails whose underside swelled downward between the supports, the famous fish-bellied rail, putting extra depth exactly where bending was worst. It helped, and it wasn't enough, partly because cast rails could only be made in short lengths, around a meter or so, which meant a track built from them was mostly joints, and every joint was a weak point waiting for its moment. The real revolution wasn't a stronger rail at all. It was a completely inverted idea. Someone asked the question backwards. What if the track stopped trying to guide the wheel, and the wheel guided itself? Move the lip off the rail and onto the wheel. Give every train wheel a projecting rim, a flange, riding along the inner face of the rail, and suddenly the rail itself is free. It no longer needs a groove, a lip, or any guiding feature at all. It can become a simple, smooth, solid shape, optimized for one job only, carrying weight. That single flip, guide on the wheel, not on the track, is the quiet fork in the road that made the modern railway possible, and it's why every train wheel on Earth today wears that hidden inner rim you've probably never noticed. But freeing the rail created a new contest. If the rail could now be any shape, what shape should it be? Britain, the superpower of early railways, went down a path that looks bizarre in hindsight. Wrought iron had replaced brittle cast iron, and British engineers developed rails with a rounded head on top. These rails were held upright, not by their own geometry, but by heavy cast iron sockets called chairs, bolted to the sleepers, with wooden or steel wedges jammed in to grip the rail. Then came a seductively clever idea. Make the rail symmetrical, a head on top and an identical head on the bottom, the double-headed rail. The logic sparkled. Once the top surface wore out, crews could simply flip the rail over and run trains on the fresh underside, doubling its life for free. It was brilliant, and it was wrong. Sitting in those iron chairs for years, the lower head got hammered and dented by its own supports, so by the time the top was worn, the bottom was already ruined. The free second life never existed. And here is the part that says something profound about institutions. Britain kept using the descendant of this design, the bullhead rail, chairs and all, as its standard for roughly a century, long after a better answer existed, right into the middle of the 20th century, purely through momentum, familiarity, and sunk cost. Stretches of bullhead track survived even longer on the London Underground and on heritage lines, fossils of a decision made when Victoria was young. The better answer, meanwhile, had already been carved, from a block of wood, on a ship. In 1830, an American named Robert Livingston Stevens boarded a vessel bound for England. He ran the brand new Camden and Amboy Railroad in New Jersey, and he was crossing the Atlantic to buy a locomotive. America had a problem Britain didn't. Iron was expensive and scarce there. Skilled foundries were rare, and thousands of kilometers of future track would have to be laid fast, cheap, and far from workshops. Every British-style chair, every casting, every fiddly wedge was a cost America couldn't afford at continental scale. So, according to the story passed down, Stevens spent his weeks at sea with a knife and pieces of scrap wood, whittling candidate rail profiles, testing shapes in miniature, searching for a cross-section that could hold itself upright with no chairs at all. What he settled on had a rounded head for the wheels, a thin vertical spine, and a wide flat base that let the rail stand on a wooden tie like a plank on the floor, needing nothing but a few spikes driven at its edges. When he landed, he convinced an ironworks to roll his whittled shape in full-size iron, and the flat-bottomed rail, the T-rail, was born. The locomotive he crossed the ocean to buy made history too. It became the celebrated John Bull, shipped to New Jersey in pieces, and it survives to this day in the Smithsonian as one of the oldest locomotives in existence. And Stevens wasn't finished, because a chairless rail needed a new fastener too. So he devised the hook-headed railroad spike, that iconic fat nail with the offset head gripping the rail's foot, an object so simple and so right that it also survives to this day. In Europe, the engineer Charles Vignol championed the same flat-bottomed concept so effectively that across much of the world, the profile literally carries his name, the Vignol's rail. Different continents, same conclusion. The self-standing rail spread because its economics were unanswerable. No chairs to cast, no keys to fit, just a rail, a tie, and a handful of spikes, which meant track could be laid quickly by small crews far from industry, exactly what a young country spanning a continent required. Yet one enemy remained, and it wasn't the shape. It was the metal. Wrought iron rails under growing traffic wore out with brutal speed, and on the busiest lines, replacement came not after decades, but after mere months. In the worst cases within a couple of years or less, an endless financial hemorrhage. Then, in the 1860s and 70s, the Bessemer process made steel cheap for the first time in human history, and the railways were among its first great customers. The results bordered on unbelievable. Where an iron rail surrendered in months, a steel rail in the same spot endured for years and then decades, and the economics of every railway on Earth were rewritten in a single material swap. Railways weren't just a customer of the new steel industry, they were its anchor client. And for years, rails were the single biggest thing the world's steel mills produced. From that point on, the flat-bottomed steel rail only grew. Rails are still classified by their weight per meter or per yard, and the story of the last century and a half is a story of that number climbing. Featherweight early sections gave way to modern main lines rolling on steel of 60 kilograms per meter and more, while the heaviest ore-hauling routes in Australia and America pushed toward 70, with special head-hardened grades reserved for punishing curves. The shape, though, the crown, the waist, the foot, barely moved. Which brings us, finally, to the promise from the beginning. Why is this the shape? Why did a profile whittled on a sailing ship conquer the planet and refuse to die? Because every zone of that strange silhouette is a separate, ruthless optimization, and it's time to decode all three. Start at the top, the head. It's thick and massive for a reason you can now guess. It is a wear reserve. Steel wheels grinding over it day and night slowly eat the metal, so the head carries years of sacrificial thickness, deliberately overbuilt so it can afford to be consumed. But its surface hides the first secret I teased. The top of a rail is not flat. It's crowned, gently domed, machined to a subtle convex curve. Why? Because train wheels are not cylinders either. Every wheel is slightly cone-shaped, wider toward the inside, and this pairing of coned wheel on crowned rail creates something close to magic. When a wheel set drifts off-center, the wheel on one side rides onto a larger diameter, the other onto a smaller one, and since both wheels are locked to one axle, the mismatch instantly steers the axle back toward the middle. The train centers itself, continuously, automatically, with no computer and no driver input. In curves, the same trick lets the outer wheel effectively become bigger and the inner wheel smaller, so the axle rounds the bend without any differential at all. And the flange, the rim everyone assumes does the guiding? It's merely the emergency backstop, screeching into action only when the geometry has already lost. On a well-matched track, the cone and the crown do the steering, and the flange rarely touches anything. That piercing metallic squeal you sometimes hear from a train dragging through a tight curve is the sound of the backstop finally earning its keep. Flange grinding against rail because the geometry ran out of room. Which connects to the second secret. Look carefully at real track, and you will find the rails are not planted vertically. Each one leans inward, tilted toward the center of the track at a precise angle, typically 1 in 20 or 1 in 40 depending on the country. That deliberate lean, called rail inclination, presents the crowned head squarely to the coned wheel tread, aligning the contact patch, taming stresses, and keeping that self-steering dance perfectly tuned. The tilt is not in the rail itself. It is built into the base plates and fastenings underneath, so every rail on the line leans by exactly the same designed angle. The entire wheel rail system is a single integrated mechanism, and half of it is hiding in plain sight under your feet at every crossing. Now the middle, the web, that thin, almost fragile-looking waist. This is pure structural mathematics. When a beam bends, the fierce stresses concentrate at its top and bottom surfaces, while the material in the middle mostly just ties the two together and resists shear. So a solid rectangular rail would squander enormous amounts of costly steel in a region doing light duty. The rail borrows the logic of the skyscraper I-beam. mass at the extremes where bending bites, a slender web between them, achieving a beam of tremendous stiffness at a fraction of the weight and price. Multiply that saving by millions of kilometers of track, and the skinny waist becomes one of the largest single acts of material efficiency in the industrial world. And finally, the foot, wide and dead flat. This is the snowshoe. All the violence gathered from the wheel above, funneled down through the narrow web, would punch straight into a wooden or concrete sleeper if it arrived concentrated. The broad base catches that force and spreads it across the full width of the tie, which passes it into the ballast, which spreads it into the earth. It's a cascade of dilution that begins at a contact patch the size of a coin and ends as a gentle pressure the ground can hold for 100 years. And as a bonus, that same flat foot is what lets the rail stand upright on its own and be fastened with nothing but simple spikes or clips, the very property Stevens was whittling toward in his cabin. One last modern touch completes the picture. Because the head's crown is functional, railways can't let wear reshape it freely, so specialized grinding trains prowl the network at night, showering sparks as rotating stones recarve the precise profile back into the steel, resharpening the geometry of that invisible steering system. The shape isn't only manufactured, it's maintained, kilometer by kilometer, decade after decade. Other inspection trains follow with ultrasonic probes, firing sound waves down through the head to hunt for invisible cracks growing inside the steel before they can ever reach the surface. So step back and look at the whole answer. A crown that steers, a head that sacrifices itself, a waist that puts steel only where physics demands it, a foot that turns crushing force into a whisper, a lean of 1 in 20 that nobody notices and everything depends on, all of it discovered through snakeheads and snapped castings and a doomed reversible rail. And all of it converging on a profile a man carved from scrap wood on the Atlantic nearly 200 years ago, a design so close to optimal that the age of computers has found remarkably little to change. The next time you stand at a crossing, look down at those two leaning ribbons of steel. You're not looking at metal lines. You're looking at one of the quietest masterpieces of engineering ever placed in public view. If this gave you a new pair of eyes for something ordinary, leave a like, share it with the most curious person you know, and subscribe, because everyday objects are full of buried genius like this, and uncovering it is exactly what we do here. Thanks for watching, and see you on the next one.